Alright, hello physics folks. This is applications of Newton's laws again. This lecture is about applications of Newton's laws, but we are looking at what we call non-equilibrium, or it's called dynamic equilibrium in the book as well. Remember, in the equilibrium case, we had zero force because we had zero acceleration. Okay, let me write that nicely. Equilibrium. So non-equilibrium or dynamic equilibrium, the same thing. This time we don't have zero acceleration. We have an accelerating object. Thus we have a net force, total force, non-zero. Then we have non-equilibrium. Approach to solutions of problems will be similar. We will have Fnet, not zero, MA is not zero. We will draw free body diagrams, apply second law, Newton's second law, and solve the problems. One very important trick I want to give you here, folks, is that take the direction of acceleration to be positive. And that will mean the direction of net force is always positive. The book doesn't do that, but I want you to use this approach because it eases a lot of algebra errors. We don't want to take A or Fnet ever negative. We'll always take them positive because we will always take the direction of A to be positive. That will cause direction of Fnet to be always positive. Okay? It could be up, down, or right, left. We will always take that positive. And applying this to questions will help us. How to apply it, how to solve it. So I'm going to dive into questions directly. Here is a non-equilibrium question. We looked at this question in equilibrium version. Now we will say, let's say it's not in equilibrium, it's moving, it has an acceleration. How do we approach it? The object with mass 1 kilogram is placed on an incline as shown in the figure above. The block is accelerating down the incline. What is the acceleration if the coefficient of kinetic friction is 0.1? So here's my situation. I will directly put my XY system here, right? Down to incline, there's an acceleration. So when I show that, I'll take down the incline to be positive direction. Alright, that will be always my choice. It happens to be the positive direction, right direction I chose before, but it doesn't have to be. In this context, Fnet equals MA context, we will always take the direction of acceleration to be positive. If it was in the other direction, I would take that to be positive. Okay, so my acceleration will always be positive again. If acceleration is in this direction, Fnet is also in that direction because it's equal to mass times the acceleration, and that will always also be positive. Again, that will help us avoid a lot of algebra mistakes. This was already my plus x direction in this case, so it's good, but it doesn't have to be. Alright, what else do we know? We have an acceleration. We have mass, so we have weight, mg. I'm going to show it here, down always. Let me do a better job here. It tilted a little bit. Alright. So this is my mg. I can directly find it if I like. 1 kilogram times 9.8. We already found it in the previous question. And it's 9.8 Newton. And there is normal force, always perpendicular to the surface. It's here. And there is friction force. Let me show that in yellow. And always against the motion. Remember, friction force. It was static friction when my object's stationary. Now I have a kinetic friction. So I'm going to call it Fk. And I'm going to stick with using the friction force with a small f here. Is there anything else? Air drag, we always ignore unless we are told to not to ignore it, right? And by the way, my y direction would be the same direction as n here. Let me also show that. Oh, no, not that. Blue. I'll stick with the color code. All right, that's my y direction. And I'm going to redraw my n on top of that actually. Here's my n. Here's my y. All right. We are accelerating. We know the coefficient of kinetic friction to be 0.1. And if that's the case, what is that acceleration? Okay. Down. I have a positive direction. All the forces in this direction will be positive and the other direction will be negative. So I'm going to mark my positive and negative forces. But remember, I told you to do one more thing in the incline question cases. Once you have your mg, you draw your mg, draw its components right away. I forgot to do it this time, but you guys don't forget, all right? We have a component along the incline and we have a component perpendicular to incline. And the component along the incline is mg sine theta. And component perpendicular to incline is mg cosine theta. Okay? And my theta here is 30 degrees. All right, now we're ready. My object is moving. Fnet is equal ma and it's not 0. All right, next step is to define my forces as positive and negative. If I look at my forces, mg sine theta is in positive direction, kinetic friction is in negative direction. I'm only interested in this direction along the incline because Fnet and motion is along there. And I'm going to write down my Fnet, which will be positive forces mg sine theta minus negative forces Fk. And that's equals ma. Solving for a, not m, I will divide each side by m or take m to the other side as division. Multiplication goes as division. And I will write down my equation for a. A is equal to mg sine theta minus Fk divided by m. M is 1 kilogram. I know that. I'm going to find mg sine theta. And that's equal to 9.8 Newton. That's my mg. Calculated up here. Times sine 30. And that should be 4.9 Newton. We already calculated that in the previous question, or you can go ahead and calculate it. My normal is equal to mg cosine theta. Notice here I'm taking a shortcut. Why? We already solved for this normal and we said it's equal to mg cosine theta because along y direction there is no motion. So along y direction there is no motion, there is no acceleration. So here actually total Fy is 0. I can apply that and I can say up forces are equal to down forces. I'm even showing that more. So this comes from the fact that total Fy is equal to 0. There is no motion along Y. Up forces are equal to down forces. Remember that. And that gives me this information here. Down force would be mg cosine theta, and up force would be n. So n is equal to mg cosine theta is the bottom line. N is equal to my mg, again 9.8 Newton, times cosine theta. And that's equal to, well, theta, let's make that 30. Theta is 30 here. And it should be 8 point, let's see what that was. .5, not 4, 5. Now, why did I need n? There's no n here. I need n for this. I have Fk in my equation to find A. And Fk, kinetic friction force, is equal to mu k times n. I know mu k now, I know n, I'll put them in here. Mu k is 0.1, n is 8.5 Newton. Remember, mu doesn't have any units. And that will give me 0.85 Newton. Now I have everybody. I have this guy, I have that guy, I know m, I'll find A. mg sine theta, 4.9 Newton, minus Fk, 0.85 Newton, divided by m, 1 kilogram. A is equal to, from there, 4.05 meters per second squared. SI unit, kilogram SI unit, I'll get A in SI units. If you want to work out the units, you will see that you will get meters per second squared. That's one example, non-equilibrium. Notice again here, along Y we have equilibrium still. Forces cancels each other because there is no motion along Y. Along X we have change in speed, acceleration, so we are in non-equilibrium or dynamic equilibrium. Here's another question. An 8 kilogram block, so we have 8 kilogram. I'm gonna put my mg down right away. 8 kilogram times 9.8 meters per second squared. That gives me Newton. Kilogram meters per second squared is Newton. And that's equal to, all right, let me find that number. 56 point, no, not that. Alright, let's guess what, I don't have it here, I'll just quickly calculate it for you. Alright, 8 times 9.8. I put the values directly in the question. Okay, 8.9.8. 8 times 9.8, 78.4. That's my weight, right? 78.4 Newton. I'm gonna check my memory here. 78.4. Forces F1 is 80 Newton and F2 is 30 Newton. I'm gonna put them in here as well. F1 is 80 Newton. F2 is 30 Newton. And I'm directly, folks, directly imagining my XY system right here. I'm gonna try to draw it with dashed lines so I won't be covering the forces here. This is Y, up is plus. For X, I'm gonna choose the direction Well, actually, let's not say up is plus. Remember, we're going to choose the direction, positive direction, to be the direction of net force in A. There's no up or down motion here, but I'm not going to say up is plus anymore. That was in only motion part. In the force solutions, we'll choose positive direction to be the same direction as A. We have freedom to do so. Okay, I put in values xy. I showed xy. Now I'm gonna continue. What is blocks moves along horizontal surface? What does that mean? It's either moving to the right or left, I don't know, but along horizontal. That means non-equilibrium well, that doesn't mean actual direct non-equilibrium. It will mean soon. Moves along horizontal non-equilibrium if A is bigger than 0. A is not 0. Okay? So I'm going to keep reading to see that. These are the forces. What is the acceleration? This tells me that I should imply there is an acceleration. So A is bigger than 0. Fnet is bigger than 0 because it's MA. And I'm going to take the direction of A to be positive. I'm not sure which direction it is moving, right or left. So I'm going to first decide that. Then I'm going to pick my positive direction to be direction of A. Okay? Theta is 45 degrees and surface is frictionless. So friction is ignored here. I'm going to ignore it. That is very important. I don't have to draw a friction force. And I'm going to see which direction the object is moving. I have 30 Newton to the left. That's along x already. To the right, I'm going to find the component of this guy. It has a component along x, f1x, which is f1 cosine theta. This is f1 cosine 45. And it has a y component upward. Fy. Now along y we have equilibrium, and there's one more force I forgot to show along y. Let me show it. That's not good. I forgot force. Normal force. If I am touching to a surface, it's always there, right? I have my normal force along y, and I know along y there's no motion. There's equilibrium along y. So along x we have a motion with acceleration. If it was a motion with constant velocity, no acceleration, it will be equilibrium. Remember that. Motion with acceleration. What do we have? Non-equilibrium. Or dynamic equilibrium, it's moving with an acceleration. Fnet along x is bigger than 0. And I'm going to define again positive direction depending on if F2 is larger or F1x is larger, because F2 is pulling to left, F1x is pulling to right? So A is asking me what is A. I'm going to get to that. First, I'm going to decide the direction of motion and pick my positive side. F2 is 30 Newton. I know that. F1x, when I put in the values, F1 cosine 45, F1 is 80 Newton times cosine 45. That will give me a value of, let me find that, 56.57. All right, that was the number. So F1x is bigger than F2. That means object is moving to the right. And I'm going to take right to be positive. I'm going to take that as positive. Again, if it was moving to the left, I would take it as positive, not right. But it's moving to the right. So positive is to the right. Now I'm going to show that here. This is the motion direction, so I'm going to take that. I'm going to say A is in this direction. I'm going to take it as positive because I always want A to be positive. Fnet will be in the same direction as well, and that also will be always positive. After that, I define my forces as positive and negative. F1x is then positive, F2 is negative. All right? And I apply my second law. Apply Newton's second law. Fnet is equal ma. Notice I'm applying this along x. I'm not calling it ax, but it's along x. I'm dropping that ax, bx idea. Aix, ay idea here as well. Fnet will be addition of all the forces I have minus in the direction. They are forces. So F1x was positive, then it will be coming as positive. F2 was negative, it will be coming as negative. Alright? And that's equal to m times a. And from here, I'll solve for a, which will be by dividing each side by m. I'll have a is equal to F1x minus F2 divided by m, the mass. When I put in all the numbers, F1x is 56.57 Newton. F2 is 30 Newton divided by the mass, 8 kilogram. A is equal to 3.32 meters per second squared. Alright, I got this weight here. I didn't even need it. That was an extra work for this part, but I don't mind because I will need it here. Part B tells me what is the acceleration of the system. What is the acceleration of the system if the surface has friction and the coefficient of kinetic friction is 0.3. Here I should have actually given the direction of motion. It's assumed that it's to the right again. I should have given if the object is moving to right. It is important here, so I'll put it here as a note. Assume object is moving towards right or to right. Okay, so if it's moving to right, A is to the right, and we take it as positive. All the same thing we have here, F1x 56.57 Newton. We calculated that. We have here mg, and mg was 78.4. We calculated that. We have normal. I am imagining XY system here as I put in the previous, but I'll avoid clutter by dropping them. Keep in mind. Up I have N, normal force, and I also have X components of, okay, let me do a better job with N, and that X component. I'm gonna use straight lines here. I'm gonna put N here. Notice I'm moving them around a little bit. That's always okay. And I'm gonna put F1y here. And let's redraw F1x too. Again, imagine the XY system here. All right. This is my normal. Oops. And this is my F1y. I know it's F1 sine theta. I showed everything now. What I'm looking for is the acceleration again. But this time we have friction. Friction is not ignorable. We have mu kinetic friction because the object is moving, and mu kinetic to be 0.3 given. If the object is moving to the right, friction is to the left, which is why you have to be given the direction of motion in this case to be able to solve the problem. You have to define the direction of friction or frictional force. So Fk is to the left. Now I showed all my forces. I'm looking for A. It's along X. So I'm going to apply Newton's second law along X. I'm going to go for just Fnet is equal ma. Keep in mind, folks, these are all X directions and position directions. Along X, we're applying it. And I'm going to look at the forces along X. Those to the right will be positive. Those to the left will be negative. So F kinetic friction force, and F2 are negatives. F1x is positive. My Fnet then will be F1x minus F2 minus kinetic friction force, and that is still equals to ma. So what is changed in this case is force is changed. My equation is the same. This general equation always holds. When I solve for a, I divide each side by m, and I'm going to have this a is equal to F1x minus F2 minus kinetic friction force divided by m. Now, let me change my color here. We know F1x, we calculated that 56.57 Newton. I forgot 7 here. And let me redo that. And use blue. All right, and let me quickly actually check that to be correct. 56.57. Good. And F2 is known. F2 is 30 Newton. We don't know Fk. We'll find that it's always mu k times the normal force. But we don't know the normal force. Normal force we find, apply equilibrium condition along y. How do we do it in a simple case? And why do I think there's equilibrium along y? Because the object is only moving along horizontal. There's no motion along y, stationary along y. So I can say safely up forces are equal to down forces. This is a shortcut of applying Newton's second law in an equilibrium conditions. Total Fy is equal to 0. Okay, shortcut, and it's pretty easy to see what are forces up. N and F1y, so N plus F1y are equal to down forces mg. Now I can solve for n. I'll take this F1y to the other side. Normal force is equal to mg minus F1y. What is F1y? Let's solve it right over here. That's a simple matter for us. That's a component. We know it, and it's F1 sine theta. It's not 56. F1 is 80 Newton times sine 45, and then you do that, you'll find the same number, 56.57, because sine 47 is equal to cosine 47. Input that in here and mg in there. You'll find n. Mg was 78.4 Newton. F1y is 56.57 78.57 Newton. And the result of that should be, checking to see if I have a number here for that. Actually, I don't. I'll just go ahead and find that. So 78.4 minus 56.57. Let's find that. That guy minus 56.57. 21.83. All right. Now I'm going to put them all in here. So A is equal to F1x No, we're not ready yet. We're not ready yet. We'll put this guy here, right? So Fk is the one we need. Fk is equal to, I'm going to go back to red here actually. Fk is equal to mu kn, right? We find that. And that guy will be inputted in here. We know this, we know that, and we'll be solving. Mu k is 0.3, n is 21.83 Newton. So my kinetic friction force in this case is, I'm trying to see if I have that. Yes, 6.55. All right, now I know this guy, 56 point, not 51, 56 point, I'm going to delete that. All right. 56.57 Newton minus F2, 30 Newton, minus kinetic friction force, 6.55 Newton, divided by mass, 8 kilogram. I'm actually gonna, oops, not that, carry this dude up here to give myself a bit space. And I'm only gonna put A here, the value of A, folks. And it should be 2.5 meters per second squared. Now remember, assessing part, I'm going to think about here, like there's friction and acceleration should be less than there's no friction case, right? Friction would slow us down a little, make the acceleration less. Did I get it less? Yes. Previous was 3.32 meters per second squared. Now I got 2.5 meters per second squared. All right, one last question, and it's about when we have objects in contact and we're pushing one of them, how that force would be carried over to the other and so on. And if we have a system with more than one masses, how do we approach these type of problems? Problem here is this, as you see in figure. We have two masses. A force is applied to them, which is given as 20 Newton. Mass 1 is, oh, I forgot the list of mass 1, mass 2. They should be 5 and 15 kilogram. Mass 1 is 15 kilogram. And mass 2 is 5 kilogram. All right. We're pushing them to the right. Surface is frictionless. So don't worry about the friction. If we push them to the right, they will go to the right. This is A. This will be my plus direction. Fnet will be in this direction. Fnet is actually only F in this case because there's no friction. If there was friction, I would say it would be against the motion. There's no friction. All right. First part of this question tells me what is the acceleration. And for that, I use Fnet is equal ma. But I'm going to say here m total times A when I have more than one masses, okay? So M total is simply addition of these masses. Think about this situation here. If I'm pushing on M1, M1 will push on M2 and they will move together. Move together means they will have the same acceleration. This guy will accelerate with A, and this guy will also accelerate with A. All the same acceleration because they're moving together, right? And that's it. My Fnet is F. It's positive to the right. We took this to be positive direction. And it's equal to m1 plus m2 times the acceleration. To find the acceleration, I divide each side by m1 plus m2 because I want to leave acceleration alone. And I'll find my acceleration. If I had 10 masses here, I would add them to m1 plus m2 plus m3 plus m4 plus up to 10. All the masses should be added, and if they're moving together, all of them will have the same acceleration. Okay, so A is equal to F divided by m1 plus m2. Let me rewrite this. So it will be 20 Newton divided by 15 kilogram m1 plus 5 kilogram. That's 20 over 21 meters per second squared. Okay, that's it. Now B. Find the force exerted on m2 by m1. And I'm going to call the force exerted on m2 to be F2, the force on 2. There are different notations. Book use F1 on 2 and so on, but I'll go with that. Each force will be named by the mass that it is applied to. So the force applied to m2 is F2. Who applies F2 is mass 1. But I'm going to show this. Mass 1 applies a force on mass 2, right? And that's F2. Mass 2 applies an equal and opposite force on mass 1 because these are actually action-reaction forces. So F1 is equal to minus F2. Okay? So how do I solve for these questions? What I want to do is I want to imagine these masses to be separated. Okay? And draw them separately. I'm going to go the line here, and I'm going to draw mass 1. They are not separated, but I am imagining them separated. Let me use actually black here. So I'm drawing my mass 1 is a bit larger than mass 2. And imagining they are separate just to be able to show what forces are on each mass separately. What is pushing on mass 2 and what is pushing on mass 1. Right? So this is my m1 and this is my m2. And if I look at the forces, whatever force is touching to my mass is pushing it. So F is only pushing on mass 1. Oops, I'm going to use blue here. Blue. So F, 20 Newton, is only m1. And then F1 is on it too. M2 applies that force to it, right? Pushes back on M1 as the M1 pushes on M2. On M2, I only have one force, and that's F2 applied by M1 mass 1. Now I'm going to write down forces. This guy is F, I know that, 20 Newton. This guy is F1, I don't know it, but I know it's equal to minus F2 because these two guys are action-reaction pairs. Which law is that? Third law, right? When you act on something, it reacts, the force you act with is equal to the reaction and opposite in direction. So Newton's third law tells me these are action-reaction forces. F1 is equal to minus F2. One more information I have is that each of these mass separately has A as acceleration. So A1 is equal to A and A2 is equal to A. Okay? And I got A, 1 meters per second squared. Now find the force exerted on M2 by M1. This is my system. I tried to pick another color here. Okay. To do that, find the force applied to M2 by M1. I'm again gonna call this F2. I'm gonna apply Newton's second law to M2 separately. Okay? Apply Newton's second law to M2. And I'm gonna rewrite it as F net 2 is equal to M2, A2. I know A2 is equal to A. I know M2 is 5 kilogram. F net 2 is F2 only. There's no other force in here. So you'll say F2 is equal to M2, A2. A2 is equal to A. M2 is 5 kilogram. A2 is equal to A, 1 meters per second squared. My question is solved. F2 is equal to 5 kilogram times 1 meters per second squared. 5 kilogram meters per second squared, and that's Newton. All right, that's F2. C, find the force exerted on M1 by M2. That's already found. We say F1 is equal to minus F2, right? Equal and opposite in direction, equal in magnitude. So I can say magnitudes are equal. 5 Newton, direction to the left, negative. You guys can call it minus 50 as well. Not 50, 5 Newton. But I'm just writing down the magnitude when I say to left, or put negativity. All right, D. Find the total force exerted to M1. If I look at M1 here, I'll solve D here actually. I'm going to separate my M1. Let me do this. Remember, we are separating the object that we are interested in. What are the forces? F net 2, I'm going to call that. That's M2A. And F net 2 will be 20 Newton. That's all I'm looking for here. Minus 5 Newton. 15 Newton. That should be M2 times A. I know A is 1, M2 is 15. It also gives me a nice way to check if I did this right. And I did it right. 15 Newton force applied to, this is my F net, applied to 15 kilogram will give it 1 meters per second squared acceleration. That's all, and I'll see you in another video where more examples are solved on equilibrium and non-equilibrium. Make sure you also watch that. See you in the next video.